Okay, welcome. We are looking at section 5.2. I'm just going to cover problems 10, 12, and 14 during this short video. And as you can see, we got some different directions for number 10. In exercise 9 and 10, we have some defined interval. For our cases, number 10, we're defined from 1 to 3. Let point A, be the coordinates where we put A in, 1 in. In this case, we're going to put in 1, we're going to get out 0. And B, be the second end of our interval, of our curve. We're going to put in 3 and get 3 square root of 2. We're to write an equation for the secant line and a tangent line to F in the interval AB that is parallel to the secant line AB. So, a lot going on there. But here's what we've got. I'm going to draw a quick sketch. I've got graphing room off to the right, but because we're only dealing with 1 through 3, I think I'm just going to use my little auxiliary graph sheet that we have on here. So I'm going to make a quick little sketch here for our graph. And we're just dealing from 1 to 3. So I will begin this by, let's go ahead and find f of 1. Well, f of 1 is clearly square root 1 minus 1 is 0. F of 1 is 0. Put in 1, get out 0. And then f of 3. F of 3 is square root of 3 minus 1, which is square root of 2, about 1.4. So we are about right in here. And I know enough about a square root function that it's going to look like that. Actually might go right through that point. But anyway, we got a point that's just from here, a curve that is really just defined right in here. Our domain is set in that region. And we are supposed to go back, we're supposed to find the equation of the secant line. So our secant line goes through the points 1, 0 and 3 root 2. Therefore, it has a slope of root 2 minus 0 on 3 minus 1, 2. Therefore, that equation could be written as, so here's my equation of line AB, our secant line. It could be written as y minus 0 equals slope root 2 on 2 times x minus 1, or because we're halfway there to slope-intercept, maybe y equals root 2 on 2x minus root 2 on 2. And that is the equation of this secant line. And our next job is to write an equation of the tangent line to F in the interval AB where it's parallel to AB. So somewhere in here, and this isn't going to be exact because I didn't draw this curve exact, but somewhere in here we can see there would be a tangent line that would be parallel. Mean value theorem assures that. So I'm going to go ahead and find our slope formula for this. I'm going to go ahead, I think I'll put it over here. F prime of x, if I treat this as x minus 1 to the 1/2, that is 1/2 times x minus 1 to the negative 1/2 times the derivative of x minus 1, which is 1, or we get 1 on 2 times square root of x minus 1. And mean value theorem tells us that somewhere this has to equal that. It actually always uses value c, so I'm going to say f of c, which is, let's do that again, 1 on 2 times square root of c minus 1 must equal root 2 on 2. So I think I'll just I'll go ahead and cross multiply, no big deal. I get 2 times root 2 times root c minus 1, a little ugly, equals 2. Divide both sides by 2, and I get square root of, so the 2's cancel, I get square root, I can combine this 2 in here, 2c minus 2 equals 1. If I square both sides, I get 2c minus 2 equals 1 still, and therefore I get c equals add 2, I get 3, divide 2, I get 3/2. Double check, make sure that's in that interval, and 3/2 is in the interval from 1 to 3. So my tangent line would be defined when c is 3/2. I just need f of 3/2, because it's going to be y minus something equals, I'm going to have the same slope, root 2 on 2 times x minus 3/2. So f of 3/2 is square root of 3/2 minus 1, or square root of 1/2, or root 2 on 2. So there's our tangent line. Very good chance that back of the book answer might have that in slope-intercept form, but at no place here did it ask us to do that. Okay. Then let's take a look at number 12 here. We're just going to do some calculator work with this one. It took 20 seconds. Pen cap here. It took 20 seconds for the temperature to rise from 0 to 212 degrees when a thermometer was taken from a freezer and placed in boiling water. Now that's going to happen very, very quickly. Obviously 20 seconds from 0 to 212. However, we need to understand the temperature didn't jump from 0 to 10 degrees instantly. It still would have gone through all values from 0 to 212, not all integer values, all values. It's going to be an increase, which in other words means that this is a continuous function. When the thermometer was taken from the freezer and placed in the boiling water, explain why at some moment in that interval the mercury was rising at exactly 10.6 feet per second. Well, let's find out what the average rate of growth was. That would be the same as what we just did with our secant line. So our average temperature growth would have been, let's clear this, it would be 212 minus 0 divided by 20 minus times 0 divided by 20. And this would be in degrees per second. And that just happens to be 10 degrees per second. Therefore, by the mean value theorem, because this would be a continuous function, the mean value theorem would state that at least at some time the temperature had to be rising at 10.6 degrees per second. So not much to that one. A little trickier when we get to number 14. 14 is going to take a little bit more reasoning, but it's a similar setup. A marathoner ran the 26.2-mile New York Marathon in 2 hours and in 2.2 hours. Show that at least twice, and when I read the mean value theorem, I don't see anything about it saying twice. It just says once. It says the marathon was running exactly 11 miles per hour. Well, let's find our average rate of speed. 26.2 miles divided by 2.2 hours, miles divided by hours, miles per hour. That is 11.9. So why must we have been running at 11.9 at some point at least twice? Well, if our runner, and this would be a written explanation, we'd obviously be talking about this 11.909. If the when the runner began the race, at the instant the runner began the race, the runner was running at a rate of 0 when the gun went off. And then the runner had to, we know, increase to 11.9 at some point. Mean value theorem says that. However, if the runner started at 0 miles per hour, we're going to have to exceed 11.9 at some point as well. And then once we exceed it, we're going to have to come back to a stop at some point after we finish the race. So we're going to have our rate fall down below that. Well, actually not really 11.9. Let's go back to the 11. We had to exceed 11 to get up to 11.9, and we really had to exceed 11.9, but at some point we would have had to come back down as we stopped at the end of the race. So that pretty well tells us that at least twice the marathoner was running at exactly 11 miles, because we had to exceed that and come back down below that. Okay, so that was quick, and we will have more to follow from section 5.2.